Okay, let's continue our discussion on stresses caused by a point load. So for this one, we're going to compute for the stress caused by a point load. What would be the stress at any point caused by a point load? So for this illustration, we're going to compute for the stress at this point due to the presence of this point load. So we have here a formula that you're going to use to solve for the stress caused by this point load at a certain area or a certain specific point. So for this one, we have here the stress caused by a point load on this area, on this point, would be equal to 3p all over 2 pi z cubed over quantity r squared plus z squared raised to 5 all over 2, or that can be specified as p all over z squared I sub 1. So our P, that is the intensity of our point load. Our Z is the distance from this surface, from this plane, where our point load will be acting, towards the point that you're going to compute the stress. Our R is this distance. This is the R that you're going to obtain. So basically, for this, you have your x and y plane. So you're going to get the value for our Pythagorean theorem. And whatever is the value, you simply have to substitute to this equation. You can get now the stress caused by a point load. Or you can have this equation. You just have the value for z and the value for I sub 1. So for I sub 1, basically, you can have those values based on this table 10.1. You just have to get the value for the ratio between R all over Z. So whatever is the value between R all over Z, you can immediately get the value for I sub 1. And if you have now the value for I sub 1, you have the value for P, you have the value for Z, you can compute now for the stress caused by a point load. So this is also a figure which gives us the value for I sub 1 with the different values for the ratio between R all over Z. So we just need the value for R all over Z, and I simply have to locate that on our figure here. You just draw a line upward. It should intersect with this curved line. As it intersects, you draw a line horizontal. You can now get the value for I sub 1. So we have here a sample problem. Consider a point load P as shown in this figure, the figure. We are given with this figure for that particular example. Calculate the vertical stress increase at Z is equal to 0, 2, 4, 6, 10, and 20 meters. Given our x equal to 3 meters and y is equal to 4 meters. So for this problem, we're going to have the value for r, small letter r, so that we can have the ratio between r all over z. So simply have Pythagorean theorem, substitute your x and y, you have the value for r, which is 5 meters. So we can prepare our solution through a tabulation. So we have our r, which is 5 meters. Our z, it varies from 0 to 4, 6, 10, and 20. So that is the depth of the point that you're going to get the stress due to the presence of the point load. Then get the ratio between r all over z. Simply have to divide that one. And once you have the value for r all over z, you can get your I sub 1 based on our table. Based on this tabulation, you can get the value for I sub 1. So, for example, we are given with what is basically needed is your r all over z. And for example, it doesn't exist. The ratio between r over z, it cannot be found here. So what you're going to do is you're going to have, you may interpolate that one. For example, what we have here is 2.5. For example, r over z is 2.5, but we don't have 2.5, we only have 2.4 and 2.6. and they have a specific value for that, you can interpolate. Then you can have the value for R all over Z, which is 2.5, and I sub 1 is 0.0034. So once you have the value now for I sub 1, for the specific value for the ratio between R all over Z, you can simply have to substitute our equation for the stress at a certain point due to the point load. This is the equation P all over Z squared I sub 1. So once you have this one, you can substitute the value for P, Z, and I sub 1, and you obtain now the specific values. These are now the stress caused by the point load at 0, 2, 4, 6, 10, and 20 meters. So that is for our sample number 1. So we move on now to vertical stress caused by a vertical line load. So basically, line load, that is a load exerted, the load exert a load along a line. So an example to that is a partition weight on the floor. So this is an illustration for vertical line load. So we're trying to compute now for the vertical stress caused by a vertical line load. You have a vertical line load here, and what will be the stress at point A due to this vertical line load? So basically for that, this will be the stress due to a vertical line load applied to the surface of intensity Q per unit length is given by this equation. So this is the equation that you're going to use so that you can compute for the vertical stress caused by a line load. So you just need the value for Q, for Z, for X, and simply have to substitute. You have now the stress caused by the vertical line load. Of course, our Q is the intensity of our vertical line load. Our Z is the distance from this surface towards the point where you're going to obtain the stress. And our X, the distance from the vertical line load towards the point that you're going to compute the stress caused by this vertical line load. So this equation can also be rewritten in this form. So this can be rewritten through this manner. So you can also have here a figure for the stress maybe non-dimensionalized. So you can have here the variation of your delta sigmas of Z with respect to Q all over Z. So these are variation for our different values for the change in stress. So we have here also a tabulation for the variation of the stress with respect to Q all over Z with a value of the ratio of X all over Z. So for this one, we just need the value for the ratio between X all over Z. You can now have the value for this expression, the change in deltas of Z with respect to Q all over Z. So we have here a sample problem. This figure shows two line loads on the ground surface. Determine the increase of stress at point A. So for this one, you are given with our two line loads. You have Q1 and Q2 having an intensity of 7.5 kilonewton per meter and 15 kilonewton per meter. So for this one, we are trying to solve for the stress at point A caused by Q1 and Q2. So basically for this, let us try to compute, so that we can compute for the stress at point A due to Q1 and Q2, we can have a summation. So first, try to compute for the stress caused by line load 1, the stress caused by line load 2. So you can have this illustration. So basically, we have here the stress at point A due to Q1, 7.5 kilonewton per meter. And this illustration, then that would be added to the stress caused by the Q2, which is 15 kilonewton per meter. So you can use our equation that was presented a while ago, which has 2q z sub cube all over pi times x squared plus z sub squared squared. So first we try to make use of our Q1, which is 7.5 in magnitude. So simply have to substitute our 7.5. Our z is 4, and our x from point A towards Q1 is 5. So simplify, you have 0.182 kilonewton per meter squared. And for the stress caused by Q2, so our Q2 is 15. Our z is 4, of course. Our x from Q2 towards point A is 10. When you simplify this one, that is 0.045 kilonewton per meter squared. And when you try to summarize this one, when you try to sum up this two, you can have now the value of the stress caused by the vertical line load is 0.227 kilonewton per meter squared. So now we move on to the vertical stress caused by a horizontal line load. So for this one, this is an illustration now for a vertical stress caused by a horizontal line load. So we have here a horizontal line load. So of course, horizontal line load that is along x direction. It is directed along x direction. So what would be the stress at point A due to this horizontal line load? So we are given with our x from the horizontal line load towards point A, and of course our z, that is the depth of point A. So to solve for this vertical stress caused by horizontal line load, you can make use of this equation. And we have here a variation of your sigmas of delta z with respect to q over z. We just need a value for the ratio between x all over z. So you have here different variation of your stresses with respect to q all over z. So we have here a sample problem. An inclined line load with a magnitude of 10 kilonewton as shown in this figure. Determine the increase of the vertical stress at point A due to the line load. So basically, you have an inclined line load, so we get now our vertical line load and horizontal line load. It makes an angle of 20 degrees with the vertical, so our horizontal line load will be 10 sine of 20 degrees, and our vertical line load will be 10 cosine of 20 degrees. So that gives us the vertical line load is 9.4 kilonewton per meter, and horizontal line load is 3.42 kilonewton per meter. So we get our, for point A, we get the value for x all over c, so that we can get now the stress caused at, at point A. So x all over c is 1.25. Based on we're going to get now the increase at point A due to the vertical line load. So basically on table point 10.2, we're only given with 1.1, 1.3. We don't have 1.25. So you get the interpolation to that, and the result for this is 0.098. Then you cross multiply so that you can get the stress due to the vertical stress, that will be equal to 0.23 kilonewton per meter squared. Now we get our vertical stress at point A due to the horizontal line load Q sub H. So we don't have, based on table 10.3, we don't have 1.25, we only have 1.0 and 1.25. You get the interpolation to that, you interpolate so that you can get this value, that is 0.0125. And you cross multiply, you have now your vertical stress caused by the horizontal line load, which is 0.107 kilonewton per meter squared. Then you try to get now the total vertical increase at point A due to the horizontal line load and the vertical line load. So you simply you sum up 0.23 and 0.107, it gives us 0.337 kilonewton per meter.